Hello guys, welcome back to my channel, and in this video is going to be a really special one because I'm going to solve what can best be described as year 2020's special infinite series. So let's get started without saying anything else. Okay, so basically the problem is, let's call it S, is defined as basically the sum from n equals 0 to infinity of 1 over n squared plus 2020 the whole thing squared. So noticing that we have a square, we can certainly try to use this difference of squares formula. So a squared minus b squared is a minus b times a plus b. So we can we can certainly attempt to use this difference of squares formula, but since we have an addition, we can convert the addition into a subtraction by introducing a special component. So we have the sum from n equals 0 to infinity of 1 over 2020 squared minus in, but the whole thing squared. And since I squared is negative 1, so in the whole thing squared is negative n squared, and that negative and this negative will make a positive. So we haven't exactly changed the meaning of our original expression. Fine, let's go ahead and express this as basically a product of two factors according to this formula. So we sum from n equals 0 to infinity of 1 over 2020 plus in times 2020 minus in. So noticing that we have product of two factors in the denominator, the greatest thing that we can do right now is perform partial fraction decomposition. There's nothing better that we can do at this point, honestly. So let's do that on a fresh page. See you there. Okay, so we basically have the sum from n equals 0 to infinity of 1 over 2020 plus in times 2020 minus in. So okay, so forget the sum for now. Let's split this up into uh, the sum of two different fractions. So originally we have 1 over 2020 plus in times 2020 minus in, right? So we want to express this as some constant a divided by the first factor 2020 plus in plus b divided by the second factor 2020 minus in. So on cross multiplication, the denominators will cancel out and we have 1 is equal to a times 2020 minus in plus b times 2020 plus in. So this can be expressed as 2020a minus ain plus 2020b plus bin all equal to 1. So notice that the only constants that we have are the 2020 and 2020b terms. So 2020 a plus b is basically the only constant we have, and the variable terms, basically n, because that was the variable, can be written as ib minus ia. So since the only constant on the left hand side is 1, Therefore, this constant factor of 2020 times a plus b must be equal to that one, which means a plus b is nothing but 1 over 2020. And since there is no n terms on the left hand side, this factor should be 0. So ib minus ia should equal 0, which means a is equal to b. So we have 2a, we can just plug it over here. 2a is equal to 1 over 2020. This means that a is nothing but 1 over 4040. And then since a is equal to b, b is also 1 over 4040. So yeah, we did all the calculation. Now let's write our sum in terms of these two quantities, in terms of our partial fraction decomposition. Okay, so this means that we can write our sum from n equals 0 to infinity as these partial fractions that we just found out. So we found out a and b to be 1 over 4040. So we can write that as a constant outside, times 1 over 2020 plus in minus I'm sorry, that's a plus over there. So we have 1 over 2020 minus in. And now let's do one thing. Let's divide everything by I, basically all these fractions. So we have sum from n equals 0 to infinity of 1 over 4040, and we have 1 over 2020 divided by I, because we plugged out an I. 2020 divided by I plus n, because we plugged an I out again, plus 1 over 2020 divided by I minus n. Well, now since it's a well-known fact that 1 over I is just equal to negative I, you can multiply and divide by I squared, you'll get negative I. So now we have the sum from n equals 0 to infinity of negative I over 4040, and then over here we can do the same thing. So we have 1 over n, and 1 over I is negative I times 2020, and we have plus 1 over negative n minus I times 2020. Well, we can just pull out the negative up front for the second fraction. So we have negative I over 4040 times 1 over n minus I times 2020 minus 1 over, now we brought out the minus up front, n plus I times 2020. So now I can divide by a minus, I can multiply by two minuses, because minus 1 times minus 1 is positive 1. So we can multiply by two minuses. So one of the minuses will go cancel out with this negative I outside to just give us an I over 4040. So we have I over 4040, and then the other negative will go inside this bracket and then flip the order of this, because this negative will be a positive and this positive will be a negative. So we have 1 over n plus I times 2020 minus 1 over n minus I times 2020. And now at this point we wait, because I mean it's not apparent what to do at this point. So we would like to make a great observation again on a fresh page. See you there. So at this point I would like to draw your attention to something that's called the digamma function of, and that's defined as, say you have a digamma of a variable, say z, that's defined as minus Euler-Mascheroni constant plus the sum from n equals 0 to infinity of 1 over n plus 1 minus 1 over n plus z, basically the variable. So notice that in our series, if you just looking at this part, since n is the summing index, z would be I times 2020, okay, and then if you look at this part, z would be negative I times 2020. So you have two of these um, series basically, which can be expressed as two digamma functions. But what's missing? We have an Euler-Mascheroni that's missing, and we have this 1 over n plus 1 factor that's missing. Because even our sum is running from n equals 0, so we don't even need to reindex that. And we can totally ignore this external factor because that's playing no role in everything here. So what we are going to do is subtract negative Euler-Mascheroni and then add negative Euler-Mascheroni, which is going to be basically like adding 0, and we're going to also do the same thing with 1 over n plus 1 term. We're going to add that and we're going to subtract that simultaneously. So we now have the sum is basically equal to 1 over 40 times the sum from n equals 0 to infinity of, well, we can actually start adding these Euler-Mascheronis and then subtracting them now one by one. So let's take this part because it already has this negative that we need. So let's consider that first. So we are having the sum of, well, we can put a negative Euler-Mascheroni plus 1 over n plus 1, and then this minus 1 over n minus I times 2020, okay, and the other part plus I times 40 of sum from n equals 0 to infinity. But notice that this does not have the negative that we need in our original definition, so we have to multiply by an extra negative, and again negative Euler-Mascheroni plus 1 over n plus 1 minus 1 over n plus I times 2020. And this totally makes sense because over here we have negative Euler-Mascheroni and over here we have negative positive Euler-Mascheroni, which will mutually cancel out. And same thing with this 1 over n plus 1 term. We have a positive here and we have a negative 1 over n plus 1 term here. So that's going to cancel out. And then we haven't changed the signs because the negative and negative will make a positive like we had over here. So because of this difference, we could add and subtract Euler-Mascheronis and this 1 over n plus 1 factor to get basically two distinct infinite sums. So now using the definition of this digamma function, we can notice that S can be written as I over 40 40 because that's the constant factor, and this part inside, what's z here? Z is just negative I times 2020 because z was whatever was added with n. So what's added with n is negative I times 2020. We have to take the negative also. So this is just going to be the digamma of whatever z we found out. Digamma of our z is negative I times 2020. Okay, and then we can take the negative outside. So we have negative I over 40 40 times, what's our z here? Z is over here in this case I times 2020, just the positive branch. So this can be written as the digamma of I times 2020. And now we can actually take some terms common like this factor of I over 40 40, and then we'll have the digamma of negative I times 2020 minus the digamma of I times 2020, and that's it. So we've successfully converted our sum into some known functions. I mean, I'm assuming you know what digamma function is. So if you don't know, the digamma of say variable z is nothing but the derivative of gamma with respect to z divided by the gamma of z. So it's basically the derivative of the natural log of gamma. These are weird functions, I know, but that's our best alternative at this point to work with. Now let's look at another interesting property of the digamma function which will be helpful in calculating what this difference of digammas is going to be. So in order to actually do stuff with the digamma function, let's look at the gamma function, and we are looking at a very specific property of the gamma function, the reflection formula which Euler proved. So say we have the gamma of z times the gamma of 1 minus z. This is nothing but, surprisingly, pi over sine of pi times z. And I'm going to make a video proving this, but until now let's just accept this fact. Fair enough, but we know this formula that say we have a gamma of 1 plus z, this is just z times gamma of z. So similarly we can write gamma of z, and we can write this 1 minus z as 1 plus negative z is equal to pi over sine of pi z, and we can use this formula on this second factor. So we get negative z times gamma of z times gamma of negative z, right, because of this formula basically, is nothing but pi over sine of pi times z. And as I said, the digamma is the derivative with respect to the variable of the natural log of the gamma function basically. Yeah. So in order to develop, get digamma in this, we need to introduce logs. So we need to take logs on both sides. So we have the natural log of negative z times gamma of z times gamma of negative z is nothing but the natural log of pi over sine of pi times z. This is not a 2, this is a z, just making that clear. So now we know this fabulous property of logs of any base, not just natural logs. So we have, say if you have log of a times b. This can be decomposed as log of a plus the log of b. So let's do that over here. We have therefore the natural log of -1 and plus the natural log of z plus the natural log of gamma of z plus the natural log of the gamma of -z. And like we have a property for when we have a product of product inside our argument, we have a similar property when we have a quotient inside our argument. This is going to be log of a minus log of b. Log of a over b is log of a minus log of b. So this becomes natural log of pi minus natural log of sine of pi times z. And now, since the gamma is the derivative of the natural log of gamma, let's differentiate both sides with respect to the argument variable, which was z. So when we do that, natural log of -1, since we are dealing with complex numbers, is going to be I pi, and this is a constant, so this will go to 0. And then when we differentiate the natural log of z, we have 1 over z plus the derivative of the natural log of gamma of z is nothing but the digamma of z by definition. And here we have negative because of the chain rule. Digamma of -z. Again, natural log of pi is a constant that becomes 0 on differentiation. And we have negative sine of pi times z in the denominator, and the cosine of pi times z times pi by the chain rule. So this now, we can just take the 1 over z on that side, because we already, if you notice, have developed this difference of digammas here. So if we have digamma of z minus the digamma of -z, that's nothing but negative. Now this will become cosine over sine will become cotangent of that angle times pi. And when we take this on the other side, we have -1 over z. And well, since there are a lot of negatives on this right hand side, let's multiply by negative on both sides. So we get the digamma of -z minus the digamma of z is equal to just the positive of this now. So pi times cotangent of pi times z plus 1 over z. Well, fair enough. That's really nice. So we have successfully developed an expression for the difference of two digamma functions, and this is an alternate version of the reflection formula for digamma functions. We already had a reflection formula for the gamma function, this basically, and we developed an alternate version of the reflection formula for digammas. So that's really impressive if you ask me. So by our mathematical adventures, we discovered this reflection formula for a digamma function, and it's actually time to apply this over, because notice that we have a difference of digammas, right? That was the original motivation for going forward with this discovery. So notice that z in our case is just going to be I times 2020, because we have a negative of z first minus the positive version. So now we can just write our sum as I over 40 times, since this fits in this form, we can write this as pi times cotangent of z is I times 2020. So we have I pi times 2020 plus 1 over I times 2020. Now, since we have a cotangent of an imaginary number because we have an I here, we have a nice formula for this. So if you have, say, the cotangent of I times some number z, that's just negative I times the hyperbolic cotangent or coth of that number. And actually the proof of this is really easy, because the cotangent is cosine divided by sine, right? And since if you want to express the cosine in terms of its exponential definition, that's going to be e raised to iz plus e raised to negative iz divided by 2, and then if when you divide by sine, it's basically multiplying by 1 over sine. So sine is basically, reciprocal of sine is basically 2i over e to the iz minus e to the negative iz. So the 2's are cancelling out. But notice that this was only for a regular cotangent of z. But instead of z, say we have I times z. If we make that change, what we get is, say, the cotangent of I times z, we get is e to the I times iz. I times I is negative 1, so negative z plus e to the negative I times I will be positive because I squared is negative 1 and a negative will make a positive z divided by, let's include this 2 for now, let's not cancel it, and over here we have e to the negative z minus e to the positive z. And now notice that this is nothing but the definition of our hyperbolic cosine of z, so cos of z, and we have I that's unused, and in the denominator we have the sinh of z, but except we have a negative sign here because the sinh of z is nothing but e raised to z minus e raised to negative z divided by 2, and we have the order flipped, so we have to take a negative for that, and this is nothing but, we can take the negative up front, negative I times cos over sinh is nothing but coth of z. Sounds like goth, but it's coth. That's where we get this formula from. I hope you're convinced. Nothing's just being randomly thrown at you, don't worry. So now let's implement this formula in the green. So we have I over 40 times negative I pi by this formula of the hyperbolic cotangent of, now we just ignore the I that was inside, z was pi times 2020, so pi times 2020, and 1 over I is negative I over 2020. And the great thing is, when you basically take the negative I, factorize that out of all the sum of these two terms, you have I times negative I, which will be minus of minus 1 because I squared is minus 1, and that will be a positive 1. So we just have 1 over 40 times pi times coth of pi times 2020 plus, now because we factorized everything out, 1 over 2020. Now it's actually trying to expand everything properly. So we've pi times coth of pi times 2020 divided by 4040 plus 1 over 4040 can be written as 2 times 2020, and this 2020 will make a 2020 squared. And when we take common denominators, we have 1 of this fraction plus 2020 pi times coth of pi times 2020 divided by the common denominator is going to be 2 times 2020 squared. Squared. So just to conclude everything, we had S, which was defined as the sum from n equals 0 to infinity of 1 over n squared. So we had the sum from n equals 0 to infinity of 1 over n squared plus 2020 squared. That's why 2020 is special. And this was just equal to 1 plus 2020 pi times hyperbolic cotangent of 2020 pi divided by 2 times 2020 squared. And now observe that, say if you want to generalize this sum from n equals 0 to infinity of having 1 over n squared plus a squared, this is just going to be 1 plus a times pi times hyperbolic cotangent of a pi divided by 2 times a squared. Basically, in the place of 2020, just replace an a, and with this we actually can find the odd inverse square series when a is 1, basically n squared plus 1 squared, which is going to look like, say, 1 over 1 squared plus 1 over 3 squared plus 1 over 5 squared, the odd inverse square series. And that is just going to be by this formula, 1 plus, in the place of a we just put 1, so pi times hyperbolic cotangent of pi divided by 2. Isn't that a remarkable result? Because that's what the odd inverse square series is equal to. And if you have the normal inverse square series from n equals 0 to infinity of 1 over n squared, which will look like 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, that is just equal to pi squared over 6 due to Euler. So there is a significant difference, although we have this pi everywhere, but there's a big difference between this series and this series. And this generalization, this 2020 special sum, makes all of that possible. So that's it for this video. So I really hope you enjoy this video, guys. Please like, share, and subscribe to my channel. Recommend me to your friends. I really need to grow as a YouTube creator. You can check out my YouTube channel with the username gamma_digamma. I make uh, math art using graphing calculators, and I'll be expanding on that in the future. In the meantime, stay home, stay safe, and peace out.